This video will show how to use exponent power rules in solving problems with Kepler's third law, something that shows up in astronomy. I have Kepler's third law written here. It's the equation that looks like p squared equals ca cubed. Johannes Kepler was an astronomer back in late 1500s, early 1600s, and in the early 1600s, through several years, many years of very hard work with observational data, he figured out this law, and we'll explain what it means here. I've got an oval drawn with an arrow down it. An ellipse is what this oval is supposed to represent, and planetary orbits are ellipses. This is one of the things that Kepler discovered. And ellipses have two dimensions that matter. They have a long dimension and a short dimension. The long dimension is called the major axis of an ellipse. And if you take that and divide it in half, you have the semi-major axis. That just means half of the major axis. And Kepler discovered that there's a relation between the semi-major axis and how long the object takes to orbit the sun. This equation is what describes that. The p is the orbital period. For what we're going to use, the orbital period we'll just measure in years. The lowercase a represents the semi-major axis of the object's orbit, and c is a constant. For what we're going to use today, the constant will be relatively simple, although it does have some units buried into it, and that's where we have to worry about the power rules for exponents. And this is what Kepler found out. P is going to be measured in years. A is going to be measured in something called astronomical units. The abbreviation for an astronomical unit is AU. The abbreviation for a year is just plain Y. It turns out that the constant C is the same for all things that orbit the sun. Kepler only studied planets, but it happens to be true for asteroids. These weren't discovered for 200 years after Kepler was working on this problem, so he wouldn't have known about them. And it's also true for things like comets. All of these things that orbit the sun have the same value for C. If we pick one particular object, we can figure out the value of that constant C. Well, the object we can use is Earth as an example. The orbital period of the Earth is 1 year. In fact, that's how we define the year. The semi-major axis of the Earth's orbit is 1 AU. That's how we define the astronomical unit as well. And so if we apply Kepler's third law to this, we can solve for C there, starting with p squared equals ca cubed. If we divide both sides by a cubed, we can find out the value of C, and it is p squared over a cubed. For the Earth, it will equal 1 year squared divided by 1 AU cubed. When I evaluate the numerator, I just get 1 year squared. When I evaluate the denominator, I get 1 AU cubed. And I'm using a rule of exponents here that when you have things in parentheses raised to a power, these are multiplied together in the parentheses. Both things are raised to the power. It didn't make any difference raising a 1 to the power. 1 squared or 1 cubed is still just 1. But this is what I get. I end up with 1 year squared per AU cubed. So there's using a power rule for exponents. And so now we know the value of that constant C. And that's the same value for all objects that orbit the sun. We can use Kepler's third law to figure out the orbital period of something for which we know the semi-major axis. And let me show you how we can do that. The planet Mars has a semi-major axis. That's the lowercase a, is equal to 1.52 astronomical units. And so I can figure out the orbital period of Mars from that. P squared equals CA cubed. The value of C is the same for everything orbiting the Sun. 1 year squared per AU cubed. We figured that out. A cubed, 1.52 AU is the value of A for Mars. I cubed that. Remember, when you cube things that are multiplied together, I will cube this number and I'll cube the units. Okay, I treat the units like an algebraic quantity. So I've got over here 1 year squared per AU cubed. The cube of 1.52, 3.51, and the cube of AU is AU cubed. The AU cubed here will divide with the AU cubed there, and when I multiply this together on the right side, what I'll have is 3.51. The units that are left are y squared. And so that's the orbital period squared. I have to do the square root on my calculator. I can imagine taking everything to a fractional exponent here. That's the same as taking the square root. And I'll have to have 3.51 to the 1/2. I'll have y squared to the 1/2. Multiply exponents. 2 times 1/2 is 1, so I'll end up with units of years. When I take the 3.51 to the 1/2, I get 1.87, and that's the orbital period of Mars. That's how long Mars happens to take to orbit the Sun. So there's an example of using Kepler's third law to figure out the orbital period of something. I'll do another video where we use Kepler's third law to figure out the semi-major axis given the orbital period. Before I stop here, I want to show you something. Occasionally you'll hear that a comet has been discovered, and I can remember this especially back in the late 1990s. There were a couple of comets that were discovered. One of them was reported to have a 14,000 year orbit. Well, how could someone possibly know that? Here's how we did that. The comets happen to have highly elliptical orbits. When the comet was discovered, it might have been there on its orbit. All we knew was that it was a comet that was at some point in its orbit. We had no idea what its orbit looked like or anything like that. A little bit later, the comet might have moved in closer to the Sun and been here. Okay, from those 2 points, you couldn't tell what its orbit looked like. If you want to know a straight line, you need 2 points, but the orbit of the comet wasn't a straight line. But if you watch the comet for a while, you can start tracing out points along its elliptical path. Turns out if you can get 3 accurately measured points along its elliptical path, you can determine the orbit of the comet, the complete shape of the orbit. I mentioned that the semi-major axis is half of the long orbit of the ellipse. Well, you watch the comet for a while, accurately measure the position. The longer you can watch it, the more accurately you can determine the position. And from that, you can get an equation for this ellipse. Know how long it is. Divide the length of that by 2, and you'll have the value of A in Kepler's third law. And then plug it into Kepler's third law, and you can solve for the orbital period. And that's how astronomers can figure out the orbital period of a comet. It may be 14,000 years. You don't have to watch it for 14,000 years, though. You just have to watch it long enough to get that orbit. When they first discover a comet, the first estimates are pretty rough for the orbital period, but as they observe it longer, they narrow down the estimate of the period and do pretty good after a while.